Hello and welcome. So, let us start from where we left. We were working out the band structure for a lattice with a basis, with 2 atom basis, and for that we set up the LCAO procedure to which is basically tight binding procedure to write down the matrix that one needs to diagonalize. Now, as we discussed in this case, the choice of the LCOA function is contains 2 parts. One is coming from lattice A and the other one is lattice point B. So, this was the lattice that I drew and so on. So, there were A and B types of atoms, and so we wrote down u m of phi m coming from A type of atoms plus u m prime phi m prime coming from B type of atom. So, this is exactly the same procedure that we followed. Now, each m denotes, so this is m equal to 1, m equal to 2 and so on. These are the unit cells, m equal to 3, m equal to 4 and so on, it goes on. So, in this case, for example, for n sites we showed that you will have a matrix of the form which can be block represented as a block matrix. So, let me just quickly go through what we did. So, we wrote down again the epsilon naught for both the atoms. We took the same because our purpose is we are looking at graphene, and so in graphene both of them are carbon atoms. For a different system where the 2 atoms are really different, one can choose epsilon 1, epsilon 2. So, that is not a problem at all. So, that was the phi m h phi m which we took to be the same as phi m prime also. But as I said that I could choose this one to be a different value, epsilon not prime or whatever, it really does not matter. The other quantity that we wrote down was minus T 1 equal to phi m h, sorry, I am not using this, I am using the bracket notation. So, let us stick to that. Could as well write it as an integral phi m h phi m prime is the. So, this means that this is the T 1 is between these two. So, that we called minus T 1, and between these we called minus T 2, that hopping is minus T 2 equal to phi m h phi prime m plus minus 1, and I chose that to be real. Again, that is an approximation that can be dispensed with, it is not necessary, but it makes life simple, that is all. I do not have to deal with mods and all that, but that is not a restriction at all, as I showed, as we have already seen in the previous case where we did 1 atom per unit cell. Okay. So, that is that is the approximation we did. We did not take any interaction, any overlap between these wave functions beyond the first neighbor, and that is all there is, and we chose them to be orthogonal, orthonormalized. And these are basically the same and similar approximations that we did for the single atom unit cell case. So, under this we have to now write the matrix in the basis of UMs, and so what we did is again a variational approach. If you just go through the variational approach, what you will end up with is this U1 prime, U2 prime, and UN U prime n for n sites will be equal to a matrix of the form that I wrote down the other day, which is epsilon naught along the diagonal, then minus T1 here, then minus T1 of course is here, epsilon naught, and this will be minus T2, these are zeros, and so on, it will go on. So, I can write, so this is minus T2, that means this also by hermeticity this will be minus T2, 0, epsilon naught, and then T1, and it goes on and on. So, then what I showed was that then what you can do is that you can identify two blocks of 2 by 2 matrices, this one and this one, and its transpose here, the transpose will appear here. So, this will become T2 0 0 0. These two, in the diagonal you will always have this red block or 2 by 2 block, and in the off diagonal you will have the so this will be epsilon naught minus T1, and you will continue doing. So, this will be the matrix. So, you can divide the matrix into these 2 by 2 blocks. Okay. So, then if you realize, then what we have achieved is that it is again a tridiagonal matrix if we can write these blocks themselves as one entity, one unit. So, this is the diagonal block, and these green ones are the 2 off diagonal blocks just after the diagonal, and nothing else survives as exactly as previous case. So, and then of course, you have this U1, U prime 1, U2, U prime 2, and so on, UN, U prime n. So, that is about the equation. I mean, that is all you need to know. So, then we defined something which we called beta, which is 0 0 minus T2 0, then beta transpose. So, I put an underline to emphasize that these are 2 by 2 matrices. So, this will be 0 minus T2 0 0. Then we had the diagonal 2 by 2 matrix, which is epsilon naught minus T1 minus T1 epsilon naught, and the vectors which I now write as C m equal to u m u m prime. And exactly as before, we will now look at the mth row, and so we will write down the equation for the mth row, but let me just write down the matrix first. Using these conventions, these 2 by 2 conventions. I also use the identity matrix, which is 1 0 0 1 in 2 dimension. Okay. Okay, so how does the matrix look like now? It is E equal to C 1, C 2, some C m, C n. Each of them is a 1 by 2 entry. It is a vector into these matrices alpha bar, alpha underline, beta transpose underline, alpha underline, then zeros all the way. So, then here you will have a beta, then you will have a alpha here, beta transposed here, again beta here, and it goes on exactly. So, this is my diagonal line, and these are the 2 off diagonals. Okay. Then again this C 1, C 2, C m, C n. So, this is the procedure. That is so now again we have a tridiagonal matrix, but each entry is itself a 2 by 2 matrix, but that is not a big complication. We have to just work with this in this 2 by 2 space, but the matrix is similar to the previous case where we used just one atom per unit cell. So, let us again do the same thing. We just assume a form which is A e to the power I m theta. Here A is a matrix again, and A is say A, I can choose this matrix as A prime. A is basically a constant. So, this in this representation, then I can write down the mth column equation for the mth column, which is E C m equal to beta transpose C m minus 1 plus beta C m plus 1 plus alpha alpha C m. Okay. Alpha is also a matrix. So, this is my equation, which is absolutely similar to the one we obtained for the LCO for 2 atoms or for n atoms, for the n atom system for in the case of 1 atom per unit cell. Okay. So, we now use this approximation, and let us see what we get. So, this will be E A e to the power I m theta equal to beta t, these will remain, then A e to the power I m minus 1 theta plus beta A to the I m plus 1 theta plus alpha a e to the power I m theta. So, I can just take out the e to the power I m theta from both sides, and the equation that I get is absolutely similar to the previous one that we obtained. So, the calculation is now basically done. What you will get is E times A equal to so beta transpose. So, let us write down beta. So, beta transpose e to the power minus I theta e to the minus I theta E times A. So, this A also I can A also I can take out. I do not need this A, but let us just keep it. I mean, the A is a matrix, so you cannot take it out that way. In the one electron case, we could easily take it out, because we just had a scalar equation, but this is a matrix equation. So, A has to be kept, but we will rearrange the matrices in such a way that we have one matrix times A. So, this is A plus beta e to the power I theta A plus alpha A. Now, remember beta transpose, what was beta? Beta was 0 0 minus 2 0. So, beta transpose, let me rewrite 0 minus 2 0 0, beta was 0 0 minus 2 0. Now, you put it in, then what you will get is basically E A equal to epsilon naught plus minus T 1 minus T 2 e to the power minus I theta minus T 1 minus T 2 e to the power I theta epsilon naught. So, that is the matrix equation that you get. So, this is basically a matrix equation of the form equal to H is basically Hamiltonian times A, where H is equal to this matrix. So, this matrix is called H, epsilon 0 minus T 1 minus T 2 e to the power minus I theta minus T 1 minus T 2 e to the power I theta and epsilon naught. So, all I have done here is that I have just multiplied beta transpose by e to the power minus I theta, beta by e to the power I theta and alpha, and sum these three matrices. These three matrices combined gives me this matrix H matrix. So, that H matrix is what I have, and I have to just diagonalize this matrix to get my eigenvalue and eigenvectors. So, I can bring this E on the right hand side, then you will get this. So, that is basically the diagonalization procedure. So, that will give me the eigenvalues E. Okay. So, what are these E's? E's are extremely easy to calculate. So, let me just write down E equal to. So, so this is obtained from epsilon naught plus minus delta, where delta is remember this e to the power I theta and minus I theta were there. So, I wrote a mod here plus minus mod of minus T1 minus T2 e to the power I theta. Okay. I can write plus I theta or minus I theta. Okay. So, this is the equation that this is that is all I need to calculate, and so this is what does this tell me? It tells me that now I have a spectrum which looks like that. So, see, this is the mod of this you have to calculate. Okay. So, the spectrum, if you do that, it will look like this. Remember, theta is again by periodic boundary condition to some k pi by n, and that k will be integer. Again, from the Brillouin zone is minus pi by a, minus pi, a was taken to be 1. So, minus pi to plus pi, and you will find that you have two energy bands because of this plus minus. You have two solutions, one is this and the other is this. So, these are the E plus and E minus solutions. As you can easily check for yourself that at theta equal to plus minus pi at these ends, two ends of the Brillouin zone, your value of delta is basically T1 plus T2. Okay. Sorry. T1 minus T2, sorry. So, this is T1 minus T2, this is also T1 minus T2. So, your there is a gap which is 2 delta equal to at that point the gap is. So, let me write at theta equal to plus minus pi 2 delta is equal to T1 minus T2 into 2 is the gap. The gap is much higher at this point, of course. Now, the interesting thing about this calculation is that now what you have is that there are, you started with 2 atoms per unit cell. So, there are 2 n states we started from. Each of these bands, this one and this one, contains n number of states. Now, how many electrons do you want to put in? So, in case for example, in the half filled system, if you have 2n number of atoms, then half filled means you can put in 2n electrons. So, maximum number of electrons you can put in, maximum capacity is 4n, right, because each of these states we can accommodate 2 electrons, but at half filling we are going to only put half of that. So, 2n electrons, basically 1 electron per side per orbital is what makes it 2n electrons, which is half filled. So, in this case what will happen? Well, you will start putting states in this green band, in the lower band, which is which is like an anti-bonding band here, which is like a bonding band here. The red is like an anti-bonding band, and this green band gets completely filled up if you are at half filling, because it accommodates n number of states, n here, n states here, n states here. So, these n states will get filled up if you have half filled system, and that is what one does for graphene. And so, once this is filled up, now you can see that this is so do not confuse this with graphene, in the sense that this band does not represent the bands of graphene. This is the system that we have just hypothetically took with 2 atoms per unit cell. We will come to graphene soon. So, then this one so this band these 2 bands have a gap. That gap is minimum gap is at the zone boundary, and the boundary of the first Brillouin zone, and that is still a finite value, which is twice T1 minus T2. If that is the case, then what will happen? You will fill up at half filling, you will fill up this band completely, the green band, and the next available state is at a gap of this value 2 T1 minus T2 mod of T1 minus T2. So, since T1 T2 are real, I chose them to be real. So, it is just 2 T1 minus T2. Now, that gap, that value is a finite value unless T1 is equal to T2, and if that value is finite, then of course, then there is a gap. That means you have an insulating system. Okay. So, and there is another thing that has happened is that there is a large amount of energy gain because the lower band has come down from the 0 energy level, or this epsilon naught is taken to be 0 here in this picture. So, I have set epsilon naught equal to 0. So, this one set of states, n states, have come down below 0, and a set of states have gone above 0, and since you are filling up only the lower band, then you have actually gained a lot of energy, because remember, to start with you had every electron at epsilon naught energy. Now, by forming the band, you have gained a lot of energy, which is every electron is gaining T1 minus T2 amount of energy, at least, if not more, because the band has a width, and so there is a huge amount of energy that this system gains in this by forming these bands. So, that is an interesting thing, and that is why the system, the electrons will form a band, and they will try to delocalize and move from one atom, one site to another, more or less try to be free as possible. Okay. So, in the next lecture, I will show you what does this mean. It means actually that there is an instability of the Fermi surface. It can lead to an instability of the Fermi surface, which is interesting, but before that I will discuss I will come back to it, but before this I will discuss the band structure of graphene and how to get the band structure, because this is just one more step to get to graphene's band structure.